Okay, thank you. My name is João Cordeiro and I came from Inesc Porto, and I'm going to present this work of rule induction for sentence reduction. It was a collaboration of three persons, myself, Dr. Gaël Dias from the University of Caen in France, and Dr. Pavel Brazil, also from Inesc Porto. The main idea of this work, which is a subtopic of automatic text summarization. So the main idea is to simplify sentences in order to improve the quality of summarization systems. It is based on the elimination of certain portions, sentence portions, which are considered irrelevant or at least not containing key aspects for the comprehension of the whole sentences. We have here three examples, and we can see that the elimination of these segments don't affect the final understanding of the sentence, and also the sentence maintain its grammaticality. So our purpose was to implement a system able to produce rules to make this work. So as main motivations, we see this work as a step beyond the pure extractive summarization paradigm, in which the summarization is made only by selecting relevant sentences. And we see this work as having several practical aspects, and I'm only here showing a few of them. As main objectives for our work, we wanted to implement a system able to induce reduction rules, and we wanted also to maintain the linguistic independence as much as possible. So we don't want to work, for example, with language thesauri and so on. Here is the main architecture of our system. So the idea is it is a kind of pipeline in which in one side enters web news texts collected automatically from the web, and then a sequence of three main processes take place in order to produce this set of rules, sentence simplification rules, which then can be applied in new summarization tasks. So I'm going to explain these three main processes, which I call here Gauss selection, instance extraction, and Aleph learning. So this first process from our system is about work already implemented and published, and I'm not going to enter too much in details here because you have the bibliographic notes and you can consult some more technical details. But I'm going to explain it a little bit in order to give the big picture, the description of the whole process. So in the first process, we intended to automatically extract a special kind of paraphrases from related web news text. As you know, in the web we can find many related news texts talking about the same event. And it is a nice place to extract a special kind of paraphrases, like this pair shown here. Our first attempt to doing this was to use already existing functions. However, we encountered some problems, and the most difficult one was this here, in which almost equal sentences were selected with these functions. So this pairs like this revealed completely useless for our objectives, for our purpose of learning reduction, of learning how to reduce sentences. So we have decided to implement a new kind of, and to propose a new kind of paraphrase extraction functions, and we defined a new type of paraphrases, or we name a new type of paraphrases, which reveal much more interesting for our learning purposes. So we name it as asymmetrical paraphrases. And what is an asymmetrical paraphrase? It's just a paraphrase in which one of the sentences is longer or contains more information than the other one. So we proposed a number of interesting functions. I'm only showing here one of them, the Gaussian functions. And as I said, I'm not going to enter in too much details here on how these functions work and why. You can just read the article, or consult this previous work of us. But the main idea here is that this kind of functions allow a certain degree of dissimilarity between the sentences, the paraphrasic sentence pair. So after extracting a huge number of paraphrases, asymmetrical paraphrases from web news texts, we employed algorithms, alignment algorithms, which are normally used in bioinformatics for the alignment of DNA sequences. We have global alignment algorithms and local alignment algorithms. And we employ them to align the words of our sentences, as shown here. We have, like in biology, we can have, excuse me, like in biology, we can have the alignment of different characters, and meaning, for example, gene mutation. And the functions we have proposed, which are the adaptation from global and local alignment to our problem, also mimic this behavior. For example, here we say that it is likely to align these two words, more likely than these two. Our alignment approach also decides in runtime which algorithm should be applied depending on the type of sentence. For example, here it is more convenient to apply a local alignment and producing these two sub-alignments. So here I'm not also going to explain more because you can have access to it in our previous work. So now I'm going to explain how do we extract some special structures that will then be used in the creation of learning instances to feed a machine learning algorithm. So from a large set of aligned paraphrases, as shown before, we take notice in special structures which we call reduction cases. Here we have two different types of structures. Here we have a rewriting case, but in this work we only focus on reduction cases. A reduction case is simply an empty sequence of words aligned, a sequence of words aligned with an empty sequence and surrounded by left and right contexts of commonly or equally aligned words. So we see this as evidence for inducing rules or patterns about sentence simplification. Another issue that we have to work with was the problem of how do we select, or at least how do we select the best reduction cases. As you can see in this example, we have 3 reduction cases. But maybe this reduction case here is not so important as this one. So we propose a function which depends on the length of the segment. Okay, the length of the left segment, right segment, and the middle segment. And with this function, we can make decisions about in which conditions we decide to extract the reduction case. In our case, we have decided to extract all reduction cases which satisfy this condition here, meaning that the length of the contexts left and right overweights the length of the middle segment. Okay. So with this, we are now able to pick these reduction cases, automatically selected from web news text, as you can see, and adapt them to be used in the learning process. Now I'm going to talk about the machine learning algorithm or framework that we used. So we decided to use an inductive logic programming approach, in particular the ALEF framework, the ALEF system. And among several important reasons, I would like to underline these three reasons. The first one, contrary to what happens, for example, in propositional learning, here we don't have to specify all the features, all the learning features prior to the learning process. So we can just specify some predicates which during the learning process decide what are the best features to work with. And the second aspect, the second reason for choosing this framework was because it is theoretical evidence saying that we can ignore the negative instances since we have a certain number, or beyond a certain number of positive cases, we can avoid the negative learning instances without losing quality. This is theoretical work from Stephen Muggleton. So, and in the ALEF framework, it is also easy to expand progressively the complexity of the learning rules by proposing more complex predicates. So here I show how do we transform our reduction cases into effective ALEF learning instances. So we have here two examples of reduction cases, and you can see that we are using three kinds of features. We are using lexical features, the words by themselves. We are using more syntactical features, the part of speech tag of each word, and we also applied a shallow parser, and here we have the shunt tags. Okay, the sentence or the reduction case is divided into several chunks, and here with colors you can see, for example, non-phrase marked with green color, and for example, prepositional phrase marked in this more red color. So these examples are transformed into ALEF terms, which are the instances that will be used for learning. And this is a 5-array term in which the first argument is just a sequential index. The second one is what we call the transformation dimensionality, which means that we have transformations, for example, in the first case, transformations from 3 to 0. And the remainder 3 arguments are 3 lists containing the information about the segments, the left, the right, and the left, the middle, and the right segment respectively. You can see that each list contains the word, followed by its part of speech tag and its chunk tag. So in ALEF, every learning process involves normally 3 files. A file in which we include all the background knowledge, a file with positive learning instances, or saying what are the positive learning instances, and one with the negative ones. So in our case, we can afford to avoid to supply or to provide this file. The idea of a learning process in Aleph is to try to find the hypothesis which maximize the hypothesis which, in conjunction with the background knowledge, maximizes the entailment of the positive examples and minimizes the negative ones. So in the background knowledge file, we can define the learning and goal and all the necessary parameters that will guide the learning process. For example, we must define the predicates, allow it to form the rules body, conditions on how these predicates will connect to each other within the rule body, and also we can define search value functions and learning constraints. I'm going to show a little bit about what we have done. So this is the header of our background knowledge file. It is automatically generated by Java program, and in the upper part here we have the definition of some general learning variables, Aleph learning variables. And below here, more importantly, this is the way, this is the process of defining the predicates that will be part of the body of our rules. So with these 2 directives, both B and determination, we are defining 3 predicates. One is the transformation dimensionality, one is the chunk tag of a given segment, and one is a kind of positional constraints, stating that, for example, in a given position of a segment, we have a given word or a given part of speech. So these are the only predicates that will form the body of the generated rules, which have this general structure, which is Horn clause. So here an example of a generated rule in Prolog format. So these rules, just to exemplify, this rule states that we can eliminate a segment of 2 words if the left and right chunks are verb phrases, and we have in the middle segment, in the second word is a noun, and in the right segment, the first word is the word to. So this is the kind of rules that are produced by the system. Here I show learning constraints that we have introduced in order to better guide and avoid some undesired rules and some rules that don't make sense. In the first block, we are saying that each segment must have some condition, left, right, or middle. And in this block here below, we are stating that we don't accept rules in which the body are formed exclusively by chunks and transformation dimensionality. So we can even improve this set of learning constraints in order to improve the quality of the rules generated. So after the learning process, big set of reduction rules are produced. I'm only showing here 3 of them and their correspondent applications. As you can see, the first 2 are well applied and produce good results. These are real rules produced from the data collected. But this last one, this third one, do not apply so well. So to assess the quality of the system, to have a first impression of the quality of the system, we took a random sample of 100 reductions So we entered reduction produced by reduction rules, and then asked two human judges to cross-rate each case in a scale from 1 to 5, where 1 mean completely wrong application and 5 is excellent. So the Cohen's kappa K agreement was 0.48, which means moderate agreement. And in terms of precision, we didn't achieve so a big difference compared to the baseline. But in terms of the utility and the application, the process of using induced rules produce a more valuable outcome. So because here is the mean of the middle segment length. So here we have some improvement, and also here this is the average number of rules fired by sentence. So this baseline is almost useless in the real data set, but here we have on average at least five rules, simplification rules, reduction rules, firing per each sentence. So to have a view about the size of the data of this experiment and processing time, because it is an important issue in Aleph. In this experiment, we worked with 90 days news stories collected automatically from the web. From this data set, we collected near 54,000 aligned paraphrases. And then we, from this aligned paraphrases, more than 13,000 reduction cases were selected. And after the learning process, 2,500 rules were produced. The induction process took around 33 minutes, which is quite good for the standards of the Aleph learning or induction times usually spent. So as a conclusion, we present an automatic, and as you can see, it is completely unsupervised as a whole. We presented an automatic system for learning rules for sentence reduction in massive real-world data sets. This is, I've shown a new approach of gathering training data for learning the system in unsupervised. The system is unsupervised as a whole, and it is highly independent from linguistic resources, and so it can be easily adapted for any language. Here I show some future work we intend to do. We are aware of some deficiencies, some problems that still exist, and certainly there are a lot of things that we want to improve in the future. And so these are some of our future research trends that we intend to follow. Thank you, and now time for questions.
Thank you. And perfect time. Questions about this work? There is a very big amount of rules. In generally, the rules are understandable for a person in order to give some guidelines for people who write. Can you read the rules or understand what the simplifications?
Yes, I think the rules are quite readable. For example, okay, here I've shown an example of a rule in the prologue syntax, but we can rewrite this in a more logical syntax, and as you can see, it is quite readable. For example, here the rule is stating some condition. I've not explained it in detail, but it says that L here means left context, R means the right context. This is the first word from the left context, must be a preposition, and here X means the middle segment. So here we have the size of the middle segment, which in this case is one word. Here is 2 words, and here is 3 words. So we have a kind of more logical representation for the rules here, and I think they are quite readable.
I mean, could we write a set of directives to the writers in order something like to say, remove the adverbs, or try to avoid adjectives before and something like that?
Yes, it's only a question of taking these rules and try to maybe generate some text specifying the information codified here.
Questions? Just one more thing.
Yes.
Do you think that the rules are type dependent? I mean, these rules were learned from news.
Yes. Genre dependent.
For PhD thesis,
Yes,
do you
yes.
think it would be?
Okay, I think that there are different kinds of text, different genres. Certainly this will be different in other types of texts. But, and maybe in other types of text, it will be more difficult to automatically collect these paraphrases. So this is a difficulty. But at least if we can achieve this collection of paraphrases, the system will learn automatically the type of rules. It will adapt to the kind of text it is reading.
Just one more suggestion.
Yes.
Normally, translators, after the first translation, have a second round in which someone make corrections, and frequently they keep the original and the corrections. It would be interesting to try to apply this to this kind of data, to a slightly different intention, but
yes, or maybe to integrate this annotation for example, having negative cases, negative instances. Yes, I think this is relevant to obtaining the feedback from users about the rules and the application of the rules and so on.
Just one question.
Yes.
On the alignments. For example, you align just like a DNA sequence, just take the original sentence and the second one. But for example, in natural language, there can be some style like passive and active voice. So if you rearrange the statements, perhaps you can get better alignments. Have you tried that?
No, we don't.
Or swapping words for style.
Yes.
Like in literature, for example, that's common.
For example, I think one example here related to what you are saying is this. For example, in this case, the second sentence here is written in differently. So what the alignment make is to decide, instead of trying to align globally these two sequences, it tries to produce sub-alignments.
Okay, so you take account of that swapping of statement. Okay.
so thank you for.
Thank you.
So, hello, I'm Filipa, and I'm here to talk about opinions. So, more specifically, opinions written on the web. And this is due to the fact that nowadays we can see that humans, when we want to gain an opinion about a certain product, we no longer depend on a small circle of known people. And in here, what we also want to do is to observe the existing techniques in sentiment analysis, so techniques that observe opinions and which ones should be used, and so this is what I'm going to talk about. So, opinions written on the web. This is an example from the Internet Movie Database, where we have 2 reviews about different movies, and we have explicit ratings, and the associated review, which is written in natural text. And one of the questions that we pose is are these opinions available on the net? Do we always have this explicit rating associated with the review? And the answer is no. Actually, even on IMDb, we can find reviews where we have no associated explicit rating. Another thing is when we aim at automatically classify reviews to obtain the opinion, so to see the overall positiveness or negativeness, we have to capture special features. In this case, they are named opinion words, which are features that gives us an insight, so they come with a feeling. And unlike category classification, where you have specific features that are highly associated to a category, in here what we see is that opinion words, for instance, in this first review, with an 8-star rating, I have highlighted in green the positive words, opinion words, and in red the negative opinion words. And we can see that in this review, you have much more negative opinion words than positive. For instance, you have the positive opinion word good, but then you have annoying, stupid, pointless, careless in a positive review. So the classifier will have to be able to overcome this type of problem. So our proposed framework, this is the overall. So what we do is we use a part-of-speech tagger. In here you used FreeLink tool. So we want to know for each word which word family belongs to. So you want to capture the verbs, the nouns, and we want to know that. Also use lemmatizers, so you can group the same word families all together. And we take under consideration the negation and neutral opinion words. So this means that we have a positive opinion word, we want to know if its polarity is being inverted. And also, the neutral opinion words are special sentences when humans do this quite frequently in reviews. So what they do is they say something like, if this product had something, and then they say a positive or negative opinion word, but it's a conditional sentence. So what we do here, we take no under consideration the opinion word which is being influenced by this neutral factor. But at this point, we capture the opinion words, at least candidates for opinion words, but we have to know which direction they're being used. So for that, we have semantic orientation algorithm, which tells us, okay, this word is being used on the negative or in the positive context. And finally, we want to know the intensity. So opinion words like good or excellent have different intensity values. And for that, you use the CentiWordNet lexicon to tell us how to do that. Finally, we use different classifiers and we compare them to see if which one is the best option to perform this type of task. Regarding the computational representation used for each opinion words. On the state of art, what we've observed is that the unigram representation presents fairly good results and is the most common used. But what we also wanted to know is, what if you use a bigram representation? So adjectives are used quite frequently to increase or decrease an opinion regarding a product. And these adjectives influence other words. So why not use this pair altogether and not apart as a computational representation, so has an opinion word. Finally, these word families are the ones that we only consider as candidates for opinion words. So all the other word families, what happens is that they have no sentiment associated to it. So they are disregarded for this task. So I've mentioned the semantic orientation algorithm. We use the one proposed by Turney. And what it does is, using a search engine, we have a candidate opinion word, and we are going to observe the number of hits. So the number of hits the Google, in this case we use the Google search engine, returns when the word co-occurs with two reference words, excellent, and this excellent represents positive polarity, and poor, which represents negative polarity. So with this, we can see how much is the word associated with a negative or positive polarity. And for this, what we also wanted to know is that this algorithm has been used and referenced quite frequently in sentiment analysis studies. But usually, most researchers use these reference words. And we wanted to know, what if you use different reference words with our opinion word? Could we actually gain better results? Our classifier will be able to perform better. So you chose a more generic opinion words, and what happens is that these words are also more generic, but they are not as strong. So the intensity factor is not as strong as excellent. If I say something like, this was an excellent movie, it's not the same as I say, this was a good movie. It's not as high. For instance, in a scale from 1 to 10, I might be in the 7 with good, but excellent is a 10. Then we used several data sets, and some of them are from the movie domain. So with these two reference words, best movie and worst movie, what we wanted to see is that if we could actually capture the orientation of a word which shifts with different contexts. So in here we want, for instance, the word horror, which in different contexts might be seen as a negative opinion word. And with this, we can actually filter and obtain the correct semantic orientation. And finally, our last proposal is to merge the domain specific, so using movie, but with the reference words proposed by Turney. So at this point, we have the direction. But this does not tell us the difference, for instance, of the opinion word excellent and good. We don't have the value for the intensity values of these opinion words. And for this, you use the SentiWordNet lexicon. This lexicon is in English language, was built based on the synsets from the WordNet, and was proposed by Sully and Sebastiani. And what gives us is, for each word, and considering the word family of that word, a value for its positiveness and negativeness. So in here, I just want to show you an example of how we're going to observe each review with these techniques. So we have two sentences, love it or hate it. And however, can someone tell me what on earth? So I'm just going to talk about the first sentence. So in the first column, in here, I'm not observing the bigrams, just show how it works with the unigrams. So we have in the first column, love it or hate it. In the second column, you have the word family. So you can see here, for instance, in this sentence, only two words will be used, because the other words belong to word families which come with no sentiment. And we can see that it are words that have no interest for a sentiment evaluation. In the third column, we have the value given by the semantic orientation, and we use the Google search engine. And in here, we can see what I've mentioned before. So an opinion word love, which should be seen as a positive word, co-occurs quite frequently in the negative context. And we saw that we have humans have a higher tendency to use positive words in negative contexts, at least with the semantic orientation algorithm. That's what we saw, so we had to do a slight shift. But it's interesting to observe this. And finally, in the last two columns, we have the positive and negative values given by the SentiWordNet lexicon. So for instance, even if we would see love as a negative word, the value, the intensity value of this word in the negative context will be none. So, as I mentioned, we want to see which techniques and which classifiers are the best to perform this task. So we chose 3 different classifiers. We chose a rule-based classifier, which is Reaper, and the support vector machines, which is well known as a fairly good classifier when we have a large amount of features. Both these classifiers, we use the Weka tool. And in here, what we want to see is, can this classifier build enough rules so we can see the difference between the positive and negative reviews? With the support vector machine, what it aims is to build decision surfaces and decide between these 2 polarities. But this is in a binary classification. But what we also wanted to do is we have, for instance, in IMDb, a rating scale that goes from 1 to 10. So for these classifiers, what we can also do is to see if we can actually evaluate individual ratings. So can I actually correctly classify rating 4? So we will perform these both evaluations. Finally, the third classifier is quite different. And the other 2 classifiers, what it does, observes the reviews as a bag of words. So this means it has no notion on the context of each sentence. And a human, when it performs an gives us an opinion, usually it begins in one sentence and ends in the same sentence, at least the opinion regarding an aspect of that product. So for that, we proposed a sentence level classifier. In here we have the semantic, the centi-word net value for that opinion word, and we evaluate each individual sentence. So with Reaper and SVM, we have a training phase and a test phase. In here, we don't have that. Okay. So it's not in a supervised evaluation. So regarding the data sets. The polarity dataset is a well-known and available dataset from IMDb. It was carefully chosen, 2,000 reviews, and they are positive and negative, and it's evenly split. So we have 1,000 positive and 1,000 negative reviews. So we extracted reviews here, so we can compare and make a more challenging task, because 2,000 reviews is a very short number of reviews for this task. Also, what happens is that on this data set, we have clearly negative and clearly positive reviews. But it's a rating scale from 1 to 10. And what we want to see is how our classifiers will behave when they will try to evaluate ratings 4, 5, 6, 7. So we extracted these reviews. But in here, we don't have an evenly split data set. So this means I do not have the same number of ratings 10s as in ratings 9 reviews. So, and for the Amazon, which is a different data set, we also have 2 data sets. These 2 were already collected and are available. And what we want to see here is with the first data set, we have 4,000 reviews, around 4,000 reviews for each domain. So what we want to see is our classifier performance able to obtain a good performance in different domains? Because in here we have movies. And we are using the Google search engine to obtain the direction of our words. Can it perform well on these 3 different domains? And also, we used another data set, which is much larger. And in here, we put all the domains all together. And we have more than 11 different domains in these reviews. And we're going to compare these results. So in here, I'm showing the results with binary classification. This is only for the SVM classifier. For each data set, we have 3 bars, which is the def score which is an harmonic measure between precision and recall. Then we have recall and precision. In here we have the polarity dataset, which is the one with 2,000 reviews. This is the IMDb extracted, where we have more than 600,000 reviews from IMDb. The Amazon S2, which is the one with the larger dataset. And then the evaluation with the dataset from Amazon, considering each individual domain. We can see that clearly the performance for the other 3 domains, which do not belong to the movie domain, is much worse. However, in here we have 11 different domains, so which also implies that maybe we don't have enough reviews to train for the classifier to be able to discriminate the important features in these domains to be able to perform a good classification. Also, there's an important factor that we observed when we did these experiments. It's that the Amazon reviews, it's a platform where people perform purchases. And when we perform a purchase, we give an insight of what we thought about that product, and we also gave an explicit rating. And this explicit rating is hidden for our classifiers, for us to be able to build in the training phase the models and then classify. But what happens is that we are seeing the explicit rating given by the user as the ground truth. And since this is a platform where we perform purchases, there are a high amount of reviews where we have high ratings and then we have spam. So we are observing the spam reviews, and we are saying, okay, this review, it's not clearly positive because we don't have clearly opinion words in that review, but the user gave a 5-star rating. And there are other issues in this type of data. However, we can see that in the overall, we had a fairly good performance with both these data sets, and with Amazon too also. But we also compared other algorithms. So as I mentioned, with the semantic orientation algorithm, we want to see different reference words. How would the classifiers perform if we can actually improve? So for each classifier, and here we have the sentence level, is a classifier which has no training phase, the rule-based classifier, and the support vector machine. For both this dataset, which is the polarity dataset, the one with 2,000 reviews, and the Amazon, we can see the SVM is the one with a higher performance, so clearly behaves much better for this type of task. And what we also observed with the Reaper algorithm is that he was not able to build enough rules to discriminate these classes. So we don't know if we required more data or if we had to capture more specific opinion words. But for instance, I'm not showing you the results for this data set, the IMDb extracted. But one of the things that happens is that we have a much larger number of reviews, positive reviews. So in this classification, what we saw is that Reaper does not struggle as hard as SVM, so he misclassifies a high number of negative reviews. So the overall performance is fairly good, but in fact, SVM is doing a better job. We have for each bar, for each classification, we have 2 bars, the unigram and bigram. So we can see that the second bar, which is the bigram representation, or we have a better performance, or is the same. So we can see that clearly, maybe you should start using more often this type of computational representation. So I'm not saying to disregard the unigram representation, but also take under consideration this pair. And finally, we wanted to see if we can actually improve the classification if we take under consideration the domain specifics, especially for the polarity dataset, which is the dataset related to movie domain, to the movie domain. But what we can see is that, okay, the results didn't improve as we expected, but there's also an important factor in this algorithm, which is when Turney proposed the semantic algorithm, he used the search engine AltaVista. And at that time, he could do something that we could not. He could say that a specific word could occur with the reference word excellent, for instance, with a maximum distance of 3 words. So when we performed these experiments, we could not be at the same situation. So what happens is that if I have a review or a page with a blog, from a blog with an opinion, so we have our words and the reference word happens 4,000 words later. And it comes as a hit. So it sees that as a co-occurrence. So we don't know if these results are due to that or not. But fact is, we cannot see any gain on using different reference words. So I've mentioned that we wanted to perform a classification, not only binary, as also a multi-class classification. So we call it multi-Bernoulli. And this is because we're going to evaluate each review for each rating. So if you have a review, we have a review from IMDb. We're going to build 10 models. We have 10 models for each rating. So we're going to obtain a rating, a prediction for each rating. So what happens here is that we're going to normalize this value. So in here we have the 10 predictions, and the one with a higher confidence will be the prediction rating for that specific review. And this experiment was performed only for the IMDb dataset and the one we had with a larger number of reviews. Oops. And in here, what I want to show is that in the first graph here, we have the 3 bars again, precision, recall, and F measure. And these are the ratings. In the overall, the performance decreased a bit. However, it's interesting to observe, for instance, these results here, because we have a high precision and then a very low recall. And what happens in this data set is that we have a high number, a really high number of positive reviews. And what happens here on these 3 ratings, we have a very high confusion. And that's why, this is a bit, okay. This is the matrix confusion. And what happens is that when you see the colors more highlighted, it means the confusion is around here. So, okay, I'll classify it's not perfect, but when it misclassifies a rating 10, does not misclassify as a rating 6 or 5, it misclassifies as a rating 9 or 8. And this also happens due to the fact of how humans expose their opinions. And we have more demanding users than others. There are no rules when we expose our opinions. And sometimes the reviews are quite similar. And finally, what I've shown here is an overall analysis on the existing algorithms. We try to compare different classifiers, use different computational representations, and what we saw is that, for instance, we should use more often this type of representation, bigram. Bigram, where you use an adjective as a first word. And there's also a gain of doing this type of classification, because in many platforms, humans use a rating scale. And sometimes we do not also offer a highly positive or highly negative. We might be okay with the product, and humans want to know that. When I want to see, for instance, a perspective on a product, it's quite odd to be excellent all the time. Maybe it's not perfect. So, as a next step, what we also want to do, Sinti WordNet is a language dependent, and it's also a static lexicon. So in this case, what happens is we have many opinion words which are highly attached to our context, and they do not exist in this lexicon. So what we are doing is to build our own lexicon based on our data. And also, semantic orientation metric, which tells us the direction. We also want to do that based on our data for the same reasons. Since, with the Google search engine, we also had another problem. It's the delay factor, because we keep performing queries to the search engine, but also the direction of an opinion word changes in the context. And we also, it's a difficult task to filter that using a technique such as the one we used. And well, that's all. Thank you.
Advantage of the order of the classes, because classifying as 1 or as 2 or as 10 is completely different if they are too far apart, but in a classification problem they are just different. I think this is just a regression problem, and can use SVMs for regression as well.
Sure. Actually, we also thought on using the version of the SVM, but well, we just didn't try.
Information about the classes, the closeness of the classes.
Sure.
Okay.
A 10 classified as 9 is a wonderful result.
We also performed from the Amazon. I didn't show here because we had a short time. With the Amazon, we had a rating scale from 1 to 5, but they weren't as relevant due to the fact that that data set was available for a study for detecting spam. So we had a lot of spam, and that wasn't our goal. And we, well, as for an accident, we were able to perform a spam detection because that was what happened with that data set.
The Google search engine for applying the Turney measure.
Yes.
I think you could perhaps explore the wildcard in Google in order to simulate the near. The wildcard is the asterisk, and I think they also have an operator, or they used to have an operator called around.
Yeah.
I don't know if you can.
At the time, I was searching to find that problem. Well, I don't know. This was a while ago, but at that time, that wasn't working. I think there are many features from Google that they deactivated. Well, but I tried to do that too.
The wildcard is working, but I'm not sure if you can simulate the exact behavior of the near operator with the wildcard, the asterisk.
Mm-hmm.
But the around, I just found out now, so I'm not sure if it works. Okay.
Hi, I don't know much about this, so I may make a completely silly question. But I was wondering, you're getting opinions, but aren't your opinions confused with the valence associated with the content of what you're writing, of the review itself? For example, if you're writing about a sad movie, then there's really negative valence, it's a very sad movie and so on, like The Notebook. And then you're extracting, like, you don't, the opinion, the negative opinion, when in reality you might love the film.
Okay. One of the reasons why we want to capture opinion words considering the context, it's due to that fact. However, we also observe that we may use negative words that might be seen as negative, but in sad movies. However, they are not the same words that we use to talk bad about movies. They are forms of expressions that people tend to be emotional when they dislike or not a movie, particularly in movies. They are different. In Amazon, the way of expressing their opinion is completely different. They're more objective.
And you can capture that.
Yeah. But what we also want to do, and it comes to that point, is that we want to, and we are performing that task right now, which is capturing the aspects of a product. Which, for instance, in the movie, we have the actors, the director. So we want to know, maybe in the overall, I enjoyed the movie, but in the review, I'm negative about for a specific actress, for instance. But I know that I'm talking bad about that actress. So the review won't be like this. It won't be an overall evaluation, but a more specific evaluation.
Sorry, do you think it would be possible to extract those domain-dependent like movies automatically?
Well, that's what we're doing. And to do that, we collected a large amount of data, and we are extracting these opinion words, which are highly associated to that specific domain. Of course, then we have one thing. We won't be transversal to a different domain. As we could see here with DVDs, music, and we only had those opinion words, they clearly perform much better in the movie domain.
One other thing, you are using Google or similar to see the polarity of words.
Yes.
Would it make sense to try to see the polarity of words in your own corpus? I mean, the huge set of the...
Exactly. The task that I was mentioning that we are doing is to obtain not only the opinion word, which is more relevant for that context, as also the direction. We are able to do using LSA for that, which helps us to detect new words and also tells us the direction of that word. Well, we're using different algorithms, I'm not going through that, but that's the whole point. Using our data for that domain so we can actually get more certainty on the direction and the intensity.
Thank you. Just a curiosity. I was wondering to what extent do you need something more apart from orientation? I mean, to what extent do you need a semantic analysis? What happens if, for example, you have someone writing something like, you cannot say that this book is not good? If you are just counting words.
Well, but LDA, what we are using, that analysis, is to expand our opinion words. So we are able to see opinions that are related, but they might not be mentioned in that specific review, but in the overall. And with this analysis that we did here, we are not able to capture that. I'm not sure if I answered your question.
Yeah. Thank you.
That's all?
I have done some experiments with a collection that may interest you. It's not so big, but it's very good for experiments, which is the quality of the food in companies in flying. They have a very small phrases that make it easier to test a few things with
data sets in that domain, they have that advantage. People are very specific, and many times it's already split by the aspects. So it has an advantage when building the model, is that I already know at least some aspects, and in this case we are using the mechanical Turk for us to be able to validate our results, because we do not have an available data set. And in the restaurants domain and for tourism, so for instance hostels, we also have aspects that are already being manually rated by the users, and that helps because we have a review, and then we have the evaluation for each aspect, so we may evaluate the more specifically. Thank you.
class imbalance, the prediction of the dementia, neuropsychological. Não sei, não sei responder a isso.
Não, este é o coisa. Não é verdadeiro.
Mas pode mudar no teclado.
Isso posso.
Consegue ir.
Okay, so I'm Sara Madeira. Thank you, Rui, for being the chair of my presentation in the talk. So I'll be presenting a work that is actually from my student, that is Cecilia. She couldn't come, so I have to replace it. And this work is part of a bigger project that is the neuroeconomics project, where we try to study neurodegenerative diseases together with the hospital in Lisbon. Okay, so what we tried to study here is what is the effect of class imbalance in the prediction of dementia, and in the particular case of neuropsychological data. That's what we have from the hospital. So this is just the outline. So basically, I will talk about the problem, a little bit about class imbalance and how it is studied, the methodology, and then I'll show you some results. So basically, all we know about Alzheimer's disease, it is the most common cause of dementia, and we know that besides the social problem that the Alzheimer's disease causes both in the patients and in the family, there is actually another problem that is the economical problem that is associated to Alzheimer's, and that's basically why in the US and also in Europe they are investing a lot in prevention. Then what we know is that if we can predict accurately what type of person will actually evolve to have Alzheimer's disease or dementia, we can work with them on prevention. So basically, about the dementia assessment, there is a clinical decision. Okay, this clinical decision is usually done using psycho exams with neuropsychological tests, and then there are more advanced techniques like cerebrospinal fluid, temporal lobe glucose metabolism, and also neuroimages, but they do not perform these more expensive exams at the hospital to all the patients. Okay? Then there are also several types of stages of dementia, okay? And the most important is what they call the mild cognitive impairment state, that is recognized to be a pre-stage of Alzheimer, and they know that people that are diagnosed with mid cognitive impairment have a higher probability to evolve to Alzheimer. And they also know that once a person is diagnosed with mid cognitive impairment, they will probably evolve to have Alzheimer in 5 years. Okay? So then we have neuropsychological problems, data, and our goal is twofold. So first, we wanted to know if we were able to differentiate the two classes, okay? Differentiate from mid-cognitive impairment from Alzheimer's disease. And this may seem trivial, okay? And for the clinicians, this is not a very important problem, because once they diagnose a guy as having Alzheimer's disease, is done, and they only diagnose a patient with Alzheimer's disease in a very, very late state, okay? So probably the guy already had Alzheimer's disease 3 years before that, when they decided to say, okay, this guy has Alzheimer's disease. So, in fact, many people that they classify as having mid-cognitive impairment are already persons that have Alzheimer's disease. And then there are several types of mid-cognitive impairment, ones that are more severe than the others. So there are guys with mid-cognitive impairments that are more likely to be normal guys with some cognitive problems due to a depression or something like that. And there are guys that really have mid-cognitive impairment that going actually to progress. So the diagnosis of mid-cognitive impairment is not itself consensual, okay? So then there's the other problem, the prognosis problem. That's the problem the clinicians are interested in. So basically, in the literature, what they've been doing is to tackle the problem of, will a guy with mid-cognitive impairment ever evolve to have Alzheimer's? And this ever evolve means in 1 year and 2 years or 5 years, okay? So what we did was a different thing. So basically, we want to know, will a person that now is diagnosed with mid-cognitive impairment have Alzheimer's disease in 2 years, in 3 years, in 4 years, or in 5 years, okay? And that's our problem, is more informative, and we use a time window approach to create the learning data set. Okay, so now the imbalance problem, as you will see, we'll have highly imbalanced data sets. So this is just how the imbalanced learning problem is defined. Basically, the goal of the classification shifts from outperforming uniformly distributed random guessing to outperforming a classifier that always chooses the majority class, okay? Because we all know that if we have a highly imbalanced problem, okay, a classifier may have a high accuracy, but in fact it's not learning anything. It's just guessing and saying that, okay, this instance will be of the class that is more frequent in the data set. Okay? So then, in the literature, there are several papers that analyze how the traditional classifiers will behave in case of imbalance. The problem is that they usually do this not in real data, but on data that they produce and where they put noise, but is all controlled. Okay, so we wanted to see, okay, in our case that we have a real data set where we have noise, we have missing value problems, and we have the problem of imbalance. Does what they say in literature about the classifiers still happens in our data or not? So basically, about the naive Bayes, they say that the naive Bayes classifier is robust, okay, and possibly with a learning bias. they see that turn-based classifier has an unpredicted behavior in case of imbalance, and that's not good. They also say that the decision trees are susceptible to misclassify in terms of this problem. And about the SVMs, they say that in case of moderate imbalance, the SVMs are robust. In case of severe imbalance, they will be all majority classifiers, so they will not work at all. Usually, they don't say what is moderate or what is severe imbalance. This depends on the paper. Okay, about the solutions for class imbalance, we have basically two types of solutions. Okay, the data level solutions, and in the case of data level solutions, what you do is that you resample the data set, okay, and then you have different types to do resample, like random, informed, synthetic, or adaptive synthetic. Usually in the literature, the state of the art is an algorithm that is called SMOTE, okay? But in this case, basically, when you give the data set to the classifier, the data set is no longer imbalanced, okay? You already dealt with the imbalance before that. And then there's the other solution, that is what we are experimenting here, that is the algorithm level or cost-sensitive solutions. So basically in this case, you don't alter the original data, okay, and you deal with the imbalance inside the algorithm. And you do this by using direct cost-sensitive classifier induction. Okay, so the algorithm should infer costs according to the imbalance. You use base risk minimization or cost-sensitive ensembles, and what we wanted to see is, according with the classifier, what is the best solution. Then, when using these algorithmic approaches, you usually have a cost matrix that is predefined or is inferred by the algorithm, and you usually use the base conditional risk, and you say that the optimal prediction is the one that minimizes the base risk, and that accurate predictions require accurate class membership probability estimates. Okay, so in this case of this type of imbalanced learning, what we call minority is our positive class, okay, and the majority class will be the negative class. So it's the other way around. Okay, so in this case we have bagging, okay, and bootstrap aggregation. What we do is to train K models on K and bootstrap samples. Then we combine prediction of models through voting. This is useful for unstable classifiers and reduces overfitting. Okay, and then there's also meta-cost. So meta-cost combines risk minimization and bagging, makes any classifier cost-sensitive with improved performance, does not require class membership probabilities, and does not rely on accuracies. Okay. So now that we know the type of algorithms that we can use, the type of strategies, we have to decide what type of metrics will be used to assess the results. Okay. So there is direct sensitivity to imbalance that can be implied in the definitions of the metrics, and there is also what we call indirect sensitivity to imbalance that can be measured using learning bias or differential propagation of errors. Then the metrics that are usually used are accuracy and error rate, ROC space metrics, especially the G-mean, and parametric space metrics, especially the F measure. So in here, I just have the formula. This doesn't matter. So basically, in the case of wording bias, we see that we have the wording bias when the true negative rate increases and the true positive rate decreases. Just the J-mean should increase. And in case of differential error propagation, basically, if the negatives are 10 times the positives, if the true negative rate is equal to the two positive rates, then what we should observe is that the negative errors are 10 times the positive errors. Okay, so this is just the F measure, doesn't matter. So basically these were the data sets we had. Okay, so we had, we split the data in two parts. Okay, one part that we used in the cross-validation, okay, the cross-validation scheme, and another part of the data set that we just rolled out to test the algorithms later once we decided what was the best strategy using the cross-validation option. And as you can see, according to the type of data we have the diagnosis problem, that is distinguishing MCI from AD, and then we have three different data sets. One where we want to predict if a guy with MCE will progress or convert to AD in 2 years, and then in 3 years and in 4 years. Okay? And also we preprocessed the data set with missing value imputation, and we performed feature selection. Okay, so this is what we used. So a 10-fold cross-validation scheme and the final validation. The costs are sought by means of the misclassification cost ratio. And then what we did was compare the base classifiers, okay, without costs, bagging, risk minimization, and meta cost. And in the algorithms we use the naive Bayes, 10 classifier, the decision trees, and SVM with kernel, polynomial kernel, and Gaussian kernel. Okay. These are the results we obtain. I'm going to talk about in a minute. So basically what we show here is the F measure over 10 cross-validation runs, okay, for each data set. And then we show the performance of the Bayes classifier and meta-learning, or ensemble method. And as I told you, the Bayes classifier is the basic method without any cost-sensitive algorithm. Okay. So then we also performed freedom tests to see if the differences in the performance we were observing were statistically significant. Okay. Just to check that. And I'm now going to just tell you what happens with the decision trees in our case. So basically we know that the decision trees are usually lack robustness to the imbalance, okay? And you might ask, okay, but if you already know that decision trees are not robust, okay, why are you using decision trees at all? Okay, And this is basically because we have a medical problem, okay? So we have clinicians, and we have to go to the clinicians, show the model, and they have to believe in the results. And it's easier to make them believe in the results if you have a tree with rules to show, so that they can understand what the classifier is doing. Or if you don't have rules or a tree, you have probabilities, because they don't understand much of probabilities, but they like it. Okay? They like rules and they like probabilities. It's harder to sell an SVM, although it might be better. Okay? So basically, what happens here is that, as you can see in the table, that is just a small part of the larger table that is above, what we see is that plain decision trees, that is the decision trees without the cost methods, were outperformed by all our methods. Okay? So if we use imbalanced learning algorithms with the decision trees, the results will always be better than if we don't use them at all. Okay? And also, the learning bias that usually the decision trees suffer from is preferably tackled through meta-costs, okay, since it led to the highest values of F measures in most data sets. Okay? In the data sets of the 3 years, where we are trying to predict if a patient will progress to AD in 3 years, meta-cost was outperformed by bagging, indicating that in this data set there is not a learning bias. Okay? So what happens in the case of naive Bayes? Okay, in the case of naive Bayes, these algorithms computes the maxima a posteriori hypothesis for the class involved, and it estimates itself the class prior probabilities and the conditions probabilities. So basically, the imbalance mainly affects the prior probabilities that are computed by the algorithm. And so what happens is that although these naive Bayesian class membership probability estimates are inaccurate, when test instances are ranked according to them, they tend to be ordered according to the class. Okay? So the decision threshold made us benefit from an adjustment, and we have seen that case in our results. Okay? So even in this case, even though naive Bayes is robust in estimating the probabilities and is robust to imbalance due to that, if you perform an adjustment, you can actually improve the results. Okay? So what happens, as I told you, is that applying risk minimization to naive Bayes was statistically superior to all the approaches. Okay, the plain naive Bayes led to the greatest F measure in the most imbalanced data sets. Okay, so when we use the data set with the highest percentage of imbalance, the naive Bayes itself outperformed all the costs that we could estimate. Okay, and then, given that bagging had no benefit compared to the other methods, including the plain classifier, that was what we expected, since naive Bayes is stable. And what we also observe is that meta-costs was always outperformed by risk minimization. And this is actually what they explain in literature, and it was what we expected. We expected because of the way the probabilities are computed in naive Bayes. Okay, so in case of the 10 Bayes classifier, the best methods were again risk minimization and meta costs, while bagging provided no benefit. Okay. In this case, what we observed is that if the minority class dependencies are incorrectly modeled by the 10-based network, shifting the thresholds do not seem to be adequate. Okay, so as you will see, the 10-based network that in literature is already said to have an unpredictable behavior. In our case, it was not that unpredictable, but still it's worse than the basic naive Bayes algorithm itself. Okay? So in the case of the support vector machine, what they say is that there are two behaviors, as I told you. In case of moderate imbalance, they are said to perform well, while in severe imbalances, SVMs are likely to classify everything as the majority classes. In our case, plain SVMs were never outperformed by the other methods, okay, indicating that, okay, they are robust, but when they fail in case of imbalance, we actually cannot improve what they do, okay? And then no methods, in case of SCM, no methods was statistical superior to the other, okay? So SVMs do not predict class membership probabilities with high accuracy, and this also means that, at least in our data set, is no worse trying to use this type of techniques with SVMs, because if they perform worse in the data set, whatever improvement we got in the prediction was not statistical significant, so it was not worth doing at all. Okay, so this is the same. Then a note on the validation results. I told you that we analyzed how the algorithms behaved in the cross-validation scheme, and then we wanted to see if now we apply the validation, we use the validation, the test set, does our conclusion still hold? So basically, the validation results were consistent to the cross-validation results, both in the decision tree and in the naive Bayes classifier, okay? And this is good because this means that we can use the type of algorithms for imbalanced data that we are advocating that are good in the case of decision trees and in naive Bayes. Okay, so the decision trees were always outperformed, and the naive Bayes was preferentially improved by risk minimization, also in the test sets. The results obtained for the 10-Bayes classifier and SVMs were not very consistent with the cross-validation results, and this is also according to what they say in the literature. They say that the 10 classifiers are unstable, and they also say that the SVMs sometimes behave good and sometimes they go for the majority. And also, since we could not improve the performance of SVM with these methods, we are basically working with an SVM that is not looking at the problem of imbalance. Okay. Moreover, what happened is that all strategies outperform strategies with decision tree as Bayes learners. Okay, so the decision trees are not very good in our problem. and combining the risk minimization with the naive-Bayes classifier achieved greater values of F measure than all other strategies except polynomial kernel SVMs, but as I told you, it's very hard to sell an SVM to a doctor. So what we decided is that given the efficient and simplicity of the combination of the naive-Bayes classifier with risk minimization, we decided that this was the solution to present to the clinicians, and we did it. Okay, so this is just an overall comparison between all the techniques that we use, and you can see this in detail in the paper if you are interested. So basically, the conclusions, okay, so we examine the effect of the imbalance of neuropsychological data on decision trees, naive-Bayes, turn-Bayes, and SVMs, okay. We had two problems, the diagnosis and the prognosis of dementia in patients with cognitive complaints. In the case of prognosis, we had 3 different time windows, 2, 3, and 4 years. Okay, the most consistent results, as I told you, were obtained for decision trees and naive-Bayes. As a consequence, and given the good performance of naive-Bayes classifier combined with risk minimization, we adopted these methods, and the method is now being tested at the hospital with new data sets. Okay. And then about future work, most of them is already done. Basically, we studied another assessment strategy that could avoid the optimism that we observed in the G-mean and complement the F measure by focusing on the majority class. We compared the results that we presented here with the resampling method, in this case SMOTE, that is the state-of-the-art on the subject, and the results with SMOTE are quite good. In the case of naive-Bayes, some of our models here are still statistically significant, but for instance, in the case of SVM, using SMOTE is very good. Okay. Then another problem, or 2 problems that we have with this data set, apart from the data imbalanced, is the high attribute dimensionality and also the high percentage of missing values. Okay, and these 3 problems should be tackled together, and we are actually doing it in order to improve the performance of the algorithms. Okay, and now I can take some questions.
First of all, you can show us the attributes, the size of data sets, how many examples do you have, how many features?
Okay, I don't know if I have...
Just tell us, though.
Okay, so about the examples, we have about 600 patients, okay? And for these 600 patients, we have follow-up, okay? And for the follow-up, we have patients with only two follow-up time points, and from 2 to 5.
Okay, maximum of 3,000 examples, if you take the 5 years.
Most of the time you cannot Actually, only now we are trying to estimate for the 5 years because we didn't have enough examples to predict that. Now that they reevaluated more patients, we are trying to predict for the 5 years. But what we can do was only to predict for the 4 years.
Okay. And how about the features? How many features?
Hundreds.
Which type of features? All propositional?
No, basically you have all types of cognitive tests. Okay, they measure if you can. They have tests where you are supposed to repeat words, where you are supposed to draw, where they measure your memory capacities. So basically, you have usually categorical features.
Perhaps numerical, how many seconds you take to make the test, or no?
They do not measure that.
Okay.
Basically, they just say, are you able to make the test or not?
Okay. You mentioned that you performed the feature selection. What are the final attributes suitable for the experts?
Yes.
Like they liked the final
Yes, actually,
attributes.
I have other slides where I can show you that, but yes.
Another point is you mentioned that as in this case of healthcare, you have to show the model to the user. But for example, you didn't use rule induction. Usually rules are very keen for understandability.
Yeah, you're
Why
right.
didn't you do that?
Because
It is in
basically because we don't have an expert on rule induction
But-
working
but-
with us. But
Just use Weka.
okay, yeah,
That's just a suggestion. Any more
could be,
questions?
yes.
Okay, I think let's thank the speaker again. This is the end of this very, very short track on bioinformatics. Thank you.